Welcome again to the electrodynamics course. The topic code is EMWG-S6. The title of the topic is Internal Impedance of a Conducting Medium. The intrinsic impedance or characteristic impedance of a non-conducting medium is found to be simply square root of the ratio of the parameters of medium, that is namely mu and epsilon. For a free space, it is equal to 377 ohm. That is the impedance Z or eta, we denote with these two symbols, both are correct, is equal to E by H, which is equal to mu by epsilon into omega, which is ohm. Now for free space, mu is equal to mu naught and epsilon is equal to epsilon naught. So we get the eta or the impedance is equal to mu naught over epsilon naught square root. If you put the value of mu naught and epsilon naught, you get 377 ohm. And the unit you can see here, if putting the electric field unit volt per meter, magnetic field intensity ampere per meter, you get volt per ampere, which is the ohm. So for free space, it is the 377 ohm. Medium is purely resistive. For free space, where the waves are propagating, the medium is offering 377 ohm. Now if a medium is a conducting one, that is having a finite conductivity, the impedance of the medium is no more pure resistive but becomes a complex factor. An expression for the impedance can be derived as follows. Considering the Maxwell equations for E and H, the popular equations, the third and fourth, the curl of E is equal to minus j omega mu H and curl of H is equal to sigma E plus j omega epsilon E, where sigma is the conductivity. So here the hint is given that you put that B is equal to B naught E is equal to j omega t is equal to E naught j omega t, and put in the respective that terms. We have done so many times, so you must be familiar with it now. So for a uniform plane wave propagating along the, let us say in the x direction this time, the yz plane of the curl of E and H can be expressed as the curl of E of yz, which is equal to minus delta Ez by delta x j plus the delta Ey by delta x k. So note that we take the curl, in the curl, the terms of Ey which vary with x. Okay, so the Ey, which is delta Ey by delta x, the vary with x, while the all other E terms considered constants and their partial derivatives are considered to be 0. So similarly, we have the curl of H yz plane is equal to minus delta H z by delta x and j plus delta H y by delta x. So we have the unit vectors corresponding to this equation number. Along with those unit vectors, we have placed the equation number 4. Now substituting equation 3 in 4, equation 1 and 2, in equation 1 and 2 respectively, what we get, delta Ez by delta x j plus delta Ey by delta x k is equal to j omega mu hyj plus hz k. Is equation number 5, where the Eyz, this is the E field plane, the plane wave given by Eyj plus Ezk, and Hyz is equal to Hyj plus Hzk. The delta Hz by delta x, similarly, that other equation is j unit vector plus delta Hy by delta xk unit vector is equal to sigma plus j omega epsilon times EYJ plus EZK. Equation, now equating this equation number 6, equating the terms in the equation 5 and 6 and rearranging and simplifying, we get minus delta hz by delta x is equal to sigma plus j omega epsilon ey, equation number 7, and delta ez by delta x is equal to j omega mu hy, this is equation number 8. So the similarly delta hy by delta x is equal to sigma plus j omega epsilon times the ez, and delta ey by delta x minus j omega mu hz, equation number 10. Now dividing equation 7 by 10, this one, the equation rather 9, I think it should be okay, 7. One is ey, this is ey is equation ey by delta x. Okay, we should have the delta ey, equation 7 is hz over hx, and this is ey, equation 7 is ey, and we take this, the term over here, it is actually equation 10 by 7, not 7 by 10. I just made the correction. If this is equation number 7, that is the ey term is here, and hz, delta hz is here, and 10 is ehz. So hz divided by ey and delta ey by delta hz, delta x are cancel out. So we are left with this equation number 11, which is j delta ey by delta hz is equal to j omega mu divided by sigma plus j epsilon omega times hz over ey. This is equation number 11. Rearranging further this equation 11, taking the ey on the one side and the hz on the other side, ey delta ey is equal to j omega mu over sigma plus j omega epsilon hz delta hz, equation number 12. Now integrating the both sides of the above equation 12 and ignoring the constants, and we get integral of ey delta ey, and so integral of hz delta hz with this term, we get the ey square by 2 hz square by 2 here, and ey by hz whole square, which is equal to j omega mu divided by sigma plus j omega, or ey by hz, which is square root of j omega mu sigma plus j omega epsilon. So this is what, this is now the E to H ratio, which is called now the impedance. Okay, so hence the ratio of the E to H is written as the Z or eta, which is equal to E by H j omega mu, because we are having this the final term j omega mu sigma plus j omega epsilon square root, equation number 14, which is now the impedance of the conducting medium with finite conductivity for good conductors. Now let's say the sigma is pretty higher, very large for the very large conductivities, epsilon mu epsilon omega, and then the expression 14 reduces to eta is equal to j omega mu by sigma. So equation 15 can also be written as, if the square root of j is replaced by 1 plus j over divided by 2 under root, then eta is equal to 1 plus j over 2 square root into times omega mu over sigma square root. Further rearranging the things, we multiply this whole term, so omega mu over 2 sigma plus j times omega mu over 2 sigma. So what we get here, that the impedance is equal to the magnitude, which is given by omega mu by sigma square root, with a phase difference of 45 degree. 1 plus j is because the a and b of the complex number, this is a complex number. If the a is equal to b, then we have the phase difference is 45 degree. So from the equation 16, it follows that the magnitude of the intrinsic impedance of a conductor is given by, this is the magnitude, which is the sigma omega eta is equal to omega mu by sigma square root. If you take the magnitude of this complex, we get, this is the magnitude, this is the magnitude, which is omega mu by sigma, with the phase difference of 45 degree. Now at a frequency of 3 gigahertz, let's now take an example. The magnitude of the intrinsic impedance for copper found to be 0.020 ohm. So eta copper for copper is equal to 0.020 ohm for the 3 gigahertz. This shows that for a conducting medium such as copper, the ratio to E to H is much less than for the free space. For a perfect conductor, sigma is infinite, and eta and eta, that is intrinsic impedance, tends to 0. Hence the E vanishes, E is equal to 0. The small value of the eta suggests that a conducting medium like copper behaves as a short circuit to the electromagnetic fields. So for this, if you consider the free space having a certain resistance, so it has a pure resistive medium, so resistive circuit is there. So but for the conductor, like this conducting medium act like, for if a field is coming, it will short circuit the whatever the voltage is applied, E is equal to 0. If you take this example to the, again we put the condition normally, the tangential component of the E is equal to 0. This is the reason for that metallics, all the metal conductors, E field, the tangential component is equal to 0. When it hits the metal surface, E amplitude of the E field function becomes equal to 0 at that particular place. So this figure shows that the field propagates in free space because of the resistive medium, and field vanishes at the surface of the copper medium or any metallic surface. So in the next slide we have the table. You can also work out. The table is also given on the website. This whole slide is, the lecture note is given. So silver, copper, aluminum, bronze, their conductivity is Siemens per meter, sigma C times the 10 to the power 7. This is 6.17 into 10 to the power 7. These are the values. This is the mu, which is constant for the we have 4 pi mu is equal to, we take the value mu naught, 4 pi into 10 to the power minus 7. Skin depth delta m is now given. The rest of the things are, you can see from the formula, are the common for the one particular frequency. We can put various frequencies and we can get the delta or the skin depth. For one example, for f is equal to 50 hertz, we can delta is equal to 9 mm, 9 millimeter, and for that particular we can take the at frequency 3 gigahertz. Rather it should be not 0.0093. okay, so for the frequency f is equal to 3 gigahertz, and for 3 gigahertz, if you put, what we get is 1.2 micrometer, which is very small, extremely small. Similarly, the impedance at various frequencies you can calculate. For 50 hertz it is 2.6 into 10 to the power minus 6 ohm, and for 3 gigahertz it is impedance is 0.02 ohm. So solve for other delta and eta given in the table, the values for again the same frequencies, that is the 50 hertz and 3 gigahertz, so that what you get eta and delta. So with this we reach to the end of this topic. Thank you very much for watching the videos.